Welcome to Quantum Kinetics First Diffusion Season 3, Episode 4. I'm here with
Bryton Rodgers, CPO of Quantum Kinetics.
Welcome back to the show, Bryton. What are we going to be talking about today?
Well, today we're going to talk a little bit about nuclear cross sections, as well as. Got to refer to my notes here. Our compound nucleus.
and you probably never even heard that word before, have you?
I had not heard that before today at all. That's a new one to me. But before we dig into those, we've got a question here from the audience. They are curious about the topic of gravity waves. Could you describe those in simple terms for somebody who's just getting into looking at this stuff and trying to figure out what's going on?
Yeah, actually, gravity is one of the most complicated and elusive concepts in all of physics, and the best way to describe gravity is some type of suction force, a negative differential pressure that pulls things in. You can push things, you can push electrons, but you can also suck electrons. And so gravity essentially is a force that shows up through a negative voltage spike that pulls things down. And anti-gravity is the antithesis or the opposite of gravity, which would be a positive light pushing away. So repulsor technology, like Iron Man's repulsor tech, would be pushing away, right? That's how he flies, is he uses a whole bunch of light that comes out of his, unibeam or pulse beam or whatever. So it's really simple. If you just want to understand what gravity is, it's just negative light. It's that simple, just negative light.
So kind of the paired force with a good example of this is some people in the past have built these little vacuum filled or emptied glass globes with a little fan inside of it that each side of the blades, they're kind of vertical and facing you. One side's white and one side's black. You shine a bright light on it and it starts spinning because the light's pressing on the
the
black or white side.
Radiometer? It's the thing that spins with the black and the white.
Right.
It spins because the radiation is pushing
in the same
pressure.
Way, yeah, exactly. So in the same way that light is applying a push to things, you're saying that gravity is kind of the complementary pull that goes along with that force.
It's really that simple because the radiometer has a white side and then a black side on each fan, right, in the vacuum tube. And if a radio frequency is coming from a tower, it'll make it rotate one direction, right? Because the waves are hitting it, causing a pressure differential in the blades themselves and they'll rotate. But if you were to pull like electricity or light away from that radiometer, it would actually spin the other way. It would start rotating counterclockwise or whatever the direction it would be.
Right. You could change that setup a little bit to get it to spin a different direction.
When you have complex concepts, it's best just to try to simplify them as possible.
I have a problem with trying to overcomplicate, but I think that helps me understand long term. But it sure makes things messy when I'm starting to learn about something new.
And that's the thing about this show is that essentially we're trying to come to you all, at the global level and teach you guys really complex things as simplified as possible. And today we're going to be talking about this crazy thing called nuclear cross-section. And that's kind of a scary word because you've probably never even heard of it. But to make it simple, to understand what a nuclear reaction looks like a fingerprint identification, is that you can have X-rays, which are the electrons renormalizing, moving, or jostling about to emit X-rays. You can also have protons that jitter during a nuclear reaction, which emit gamma rays. And so if you see an X-ray or you see a gamma ray, you're inside a nuclear cross-section. And if you see neutrons flying off, you know for sure you're in a nuclear reaction because there's neutrons actually scattering elastically and inelastically, right? So you can have these fall-off gradients, right? You can have way far away, you see lots of X-rays. Like, think of it like if you were to see a nuclear bomb go off from afar, you would feel a pressure wave. That's what the electrons would feel from far away. But in our situation, we do microscopic nuclear cross sections of like electron size scale nuclear bombs. Bop, 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 bop. Just like little tiny nuclear blasts going off inside the arc reactor fusion on demand technology. And they're super duper safe, but it's not a nuclear blast that's out of control and just one pop. It's a whole bunch of little pops. Mm-hmm. And so that's why you see these little X-ray emissions and you see gamma ray emissions, and then you also see neutron flux radiation sometimes too.
Yeah. So, and there's also the application of nuclear cross-section. I've seen that idea, I don't know if explicitly used, but when you're talking about like a fission reactor core and you're interrupting the nuclear cross-section of the fissile material. You're like pulling out the control rods so that more of those neutrons can interact. Yeah. The control rods are kind of like breaking up that cross-section, but you remove that and suddenly you've increased the size of that. Yep. And now you're getting more absorption of these energetic particles, creating more interactions, and you get this thing carrying itself away enough to the point where you're boiling water, or you get a Chernobyl event, or like there's a large range of stuff that's going on here.
Yeah, and that's the beautiful thing about cold nuclear fusion with the arc reactor technology is that we don't ever have an issue of a thermal runaway event or a nuclear runaway event because we're pulsing it, and every pulse gives us a microscopic nuclear event. It's not like, you know, you have a control rod that's going in, and if you lose control of the control rod and it falls in, or it doesn't get pulled out, or you can't get the moderators in there fast enough to slow down the neutrons, you know, as in the movie, HBO movie series called Chernobyl, they call them little bullets. The neutrons were the bullets.
Yeah.
And so, like, in our reactors, we don't have that issue. And to go about that, what you're talking about with moderators, to slow down nuclear reactions with a cross-section, what happens if you put water around a nuclear fission reactor or a fusion reactor? What happens in the cross-section there? What do you see? What's the difference?
Well, the water is a great shielding material for neutrons, so it absorbs neutrons really well. So it's got a very high nuclear cross-section, so that's what is used to determine whether a material will be a good shielding material for a particular radiation. So you'll have water or Delrin or HDPE.
Well, what is Delrin to the audience who doesn't know what a Delrin is?
It's a plastic. It's a pretty simple, common material. It's an expensive plastic, but
polymethylene or something like that, or
I don't recall. But in addition to the hydrogen carbon chain that you get, it's got a lot of oxygens in there
and
as
hydrogens.
Well, and hydrogens, and that material is a slightly better, or maybe substantially better, shielding material than just HDPE, which is basically milk jug plastic. It's funny that these common materials we're used to being around are actually extremely important for the construction of such amazing technologies like nuclear fission reactors and nuclear fusion reactors. Like, these things become very important to include.
Are you saying that a jug of milk, the plastic, is a neutron moderator?
Yes. It's certainly an absorber. You just stack up. You were talking to, or I was watching a video the other day with Dr. Max, and he had this stack of boxes of boron around his experimental setup. So
borax,
borax. So you could do the same thing with
You'd buy that
milk
at
jugs
Safeway.
full of water, and just stack those around your little reactor setup or something, and prevent neutrons from escaping into the environment from that. And
he actually uses that for gamma radiation too. And to go back to the nuclear cross section of reactions that are nuclear, you have the X-rays are associated with electrons.
Yep.
The protons are associated with gamma rays. Now, that's emission, right? They can emit that. And then the neutrons will emit neutrons, either slow, fast, or whatever.
Right.
It goes the other way too, Bryton. So, like, if you have a bunch of hydrogens, which are protons and electrons, they absorb gamma ray really well. And because water has a hydrogen and oxygen, water absorbs gamma rays really, really well because there's a lot of protons there.
So is that why Delrin's a little bit better of a shielding material, is because it'll also capture those higher energy gammas along with the neutron flux?
And that's what's great about our reactors is we've got Delrin encased around the reactor fuser,
which is filled with water.
So that's also a natural moderator. So our reactors, though they are nuclear, it's safe nuclear. It's the safest nuclear that you can get basically on the market.
Right. We're collecting all of these pretty heavy elements compared to what we're starting out with, of like just water and whatever the thing is made of, the reservoir is made of, and we're getting these heavy elements out of it. When we're doing these nuclear interactions, we're able to pick up X-rays with our X-ray detector, but when we set up our gamma or neutron detector, nothing's escaping from it because it's inherently shielded from just the water. And then we have the added safety layer of the Delrin outside of that.
And then we even have a stainless sheet around it too to collect any other radiation signatures like a radio or something like that.
Right, whatever else is coming out
because
of that
there is a radio wave being emitted as well. Okay. So when you have a nuclear reaction, even if it's like at the electron scale, think of it as like a little tiny star just goes pop, like a star.
Yeah.
You get all the radiation, some in different levels of intensity, yes, but you do get like a blast.
It's kind of statistically determined, like with everything quantum. It's kind of what are your odds? What are your probabilities of getting this, this, and this? And certain interactions have most of the radiation coming off of it in the form of a neutron or a gamma. But you're still going to be getting a lot of other stuff because those kinds of interactions tend to create a lot of
turbulence,
noise, a lot of chaos in what's going on at that scale. Yeah.
And the negative pulse that you see on the oscilloscope here is essentially a synthetic compound nucleus event that's happening from our reactors, essentially. We pulse our system in such a way to create an actual negative differential pressure in the transformer, which then the whole universe has to renormalize to that, just like a gravity field, right? Like we talked about in the beginning, is gravity is negative light and anti-gravity is positive light. So when you do repetitive compound nucleus signals into a transformer, it causes the universe to renormalize, causing fusion at room temperature.
Right. And there's another term I'd never heard before, is the compound nucleus topic. If you could dig into that a little bit, because that one's pretty new to me. I know we've discussed the oscilloscope signals that we're getting, as well as the signals that are coming through on the pulse counter for our X-ray detectors.
Yes.
Now, that same signal type doesn't happen with our other detectors when we're detecting things. So it's special with the X-ray. Right.
Because of the neutron moderator and the Delrin moderator, our gamma ray detector and our neutron helium-3 detector, though it does detect gamma and it does detect neutrons at like thermal levels that are low.
Right.
We don't see the negative compound nucleus signal. And just for the audience, a compound nucleus event is when, and it's actually Niels Bohr, he came up with it, is that when you have an atom that has a nucleus, and then you have another atom that has a nucleus, and when they come together, and then they go like this, and they cross over, and they go into a fusion type of event, that is a nuclear cross-section. And what happens is when they get excited when they first fuse, but then as they're trying to renormalize back to stability, they're vibrating. It's almost like an echo. It's like, and then it kind of goes below the stable state at what it was before. So compound nucleus goes stable state, excited fusion state, and then as it's fusing, it's ringing like a bell, ding, and then it goes below stable state and then rings out and then tries to go back to normal.
Yeah.
And we see that same signature in our X-rays. And that's, again, like we talk about nuclear cross-section. Like if you have a nuclear bomb go off, you're going to feel it from far away too, right? And all the X-rays are feeling this echo of a compound nucleus far away, just like gravity. Because of mass is pulling in and it's causing a fusion event to form a planet or a moon or whatever. It's a negative force from a nuclear reaction. It's kind of wild.
It's fascinating stuff. It's definitely outside of the normal awareness here.
And so you can see on the oscilloscope here, we have a bifouler transformer that has an iron core, just like a planet. A planet has an iron core just like this. And then on the inside of the core is you have current flow, right? Like you have magma and you have, volcanic stuff that are trying to weep out of the crust. And so this transformer is acting just like a little planet because the current is flowing through the wires and they're jostling back and forth. Like magma in a planet is not stable. It's not just a flowing thing. It's a terminative what did you call it in the episode?
Intermittent.
It's
turbulent.
It's turbulent flow.
Yeah.
So it's ringing.
Because the core and crust are spinning at different directions. So they're kind of stirring it up between those layers as it's going and making this mixing of material. And when you move around electrons, you get magnetic fields.
You get a magnetic force. And that's the beautiful thing too, is that like if I pull out the magnetic core, if I can do this without making a mess, if I pull out the magnetic core, you can see the signal changes on the oscilloscope. And if I put the magnetic core or the magnetite, essentially crystal that's inside a planet, you put it back in, you get the resonance again. And you get more the negative pulsing action, which is more of the gravity.
Yeah.
Which is pretty cool.
It is.
It all makes sense, doesn't it?
Kind of. Little bit by little bit.
Well, and here's the thing about a planet. It has a north and a south pole. This has a north and south pole too, this little transformer right here.
Which is changing.
It's
back
alternating.
and forth as it's alternating. Right.
So it's almost like there's a DC signal and then also an AC signal in here, which is really interesting. But like,
it's kind of a stacking of signals. This is another one of those places where like your ham radio operator is actually set up very well to understand a lot of these dynamics that we're dealing with.
Absolutely.
Or a radio engineer too, I guess. But we're kind of speaking to the non-professional crowd mostly.
Well, we're education, right? So that we have to speak to all levels, like from, elementary school all the way up to basically professional, professors and PhDs, which is really hard because like if I say compound nucleus, you're first of all, your brain's going to go, I've never heard that word in my life. What is that? Can you bring it down a level?
Yeah.
So
it's kind of, it's funny too. We've had some pretty funny things happen where like, you can say one moment be saying something that sounds very like technical and intelligent, then the next moment you're just like, God, did I just say that? I sounded like an idiot. What's going on here?
Well, and that's why it's so easy for people to like make fun and crack jokes at us and all that, because what we're doing here is something that is really hard. And like teaching people really complex theories and ideas and technology, it's not going to be easy. And so of course you're going to make little mistakes here and there, and it's just a part of the learning curve.
Right. And we're learning at the same time too.
I am.
It's when you're dealing with new technology, the thing about newness is people haven't been doing it before, so there's not this long history of people figuring out how to explain it in a clear and stepwise fashion from first grade to graduation. We're playing around with a lot of ideas when we're looking at these systems. And at the same time as we're trying to figure out how to express it clearly to ourselves, we're trying to share that information with you, the audience. And it's not a linear process at all.
No, especially when you're trying to build stuff at the same time.
Right.
You're learning about the technology that no one knows about, and that changes the design apparatus that you put on, the computer, or how you even pick a material. Like, all right, are we going to use Delrin on this one, or are we going to use something else like acrylic? There's all these design characteristics that you have to take into account. But which is great about our technology is that our technology uses really basic materials like stainless steel and Delrin and and acrylic. We don't use really expensive, super rare earth conducting magnets. Like we don't use super high 1 million volts, 1 million amps kind of discharging circuits. No, this is all household voltage stuff.
Yeah, this is stuff that we have built in what amounts to a bit more than a well-equipped home garage shop.
Yeah.
So
can I tell you a story?
it's a pretty wild experience to be doing like cutting edge tech, but that kind of tells the story. I think a lot of the world's major innovations come from somebody's garage.
Amazon, Microsoft, Apple, the whole thing. Like, I want to tell you a story real quick. I want to tell you a story. So I have a friend who lives in Renton, and he introduced me to this person that he knows who used to work as a nuclear submarine engineer.
Okay.
And then he went from
that's a cool guy
the Navy to, because he's super duper smart. Like his SAT scores are just like off the charts. And he then went from the nuclear Navy to Hanford as a contractor.
Right.
And I sat down with him and had some wine and, and talked to him about nuclear reactions. And I told him basically what we're doing here at Quantum Kinetics. And I told him the signatures we get the X-ray, we get the gamma, and we get the soft neutron or the thermal neutron. And he took a swig of his wine, put his cup down, and looked me right in the face and said, "That is a nuclear cross-section. You be careful around that." That's what he said.
Yeah.
And that's a nuclear engineer who was on a nuclear sub.
Right, because they know when you're getting real nuclear reactions going on because they've been dealing with it.
He's been doing it 20
and
plus
I mean
years.
you've been verifying this for 10 years.
I've seen the repercussions of it too.
Yeah. So that's the stuff to be careful around. But it's also something.
It's safe.
Yeah, it's safe because it's been built in a way to be safe, and it's also operated in a way to be safe.
Yes. And right now, we're not even operating at all. Like whenever we do an operation now that we've gotten to this level is when we're going to do an actual industry level experiment, like with a partner, that's when we do it. We don't actually do it anymore at all.
We kind of stopped
why?
experimenting in our own lab because we realized like, okay, this requires a little bit more stuff going on, and that's part of what we're excited to do when we get funded. We'll be able to build some much more involved shielding apparatus and establish much more involved safety procedures to allow us to push that edge much more as well.
Yeah, that's a good transition into the NRC 10 CFR 30 and 34 regulations for nuclear fusion reactors. That's a great segue.
Yeah. Well, that's an interesting one. Is I've been not digging in too hard. I've been reviewing along, and when I went and took a look at Washington State for the fusion industry is working, or the Department of Health for Washington State is doing, from my impression so far, an excellent job of working with fusion companies. They're trying to really enable companies to push the edge of technology while maintaining a very flexible outlook on things and maintain this goal of safety for people.
Do you want to talk?
That's what's important. And something that a lot of fusion companies, as I understand it, so far are basically registering their devices as
particle accelerators.
Right. Yeah.
Okay, so just for the audience, the NRC, which is a Nuclear Regulatory Committee or whatever, they have a regulation for particle accelerators. And the particle accelerators under 10 CFR 30 and 30.4 is that's a particle accelerator regulation. And just recently, the IAEA and the NRC have classified nuclear fusion reactors as actually just particle accelerators. Now, the definition of a particle accelerator, for those who don't know, is one, it has to do transmutation, which means a nuclear cross-section of influence, X-rays, gamma, neutrons.
And I was seeing some definition in there based upon specific energy levels of emissions. I was seeing like one was like mega electron volt plus, and I think in another place, I think I saw giga electron volt plus.
We're going to get to that in a second. This is very interesting, actually. Yeah. And then the second regulation for a particle accelerator, aka a nuclear fusion reactor, is that it accelerates, decelerates charged particles like electrons, protons, and nucleons, which is what we do with particle oscillation as an energy generator, microexcited.
And that's what you're doing when you compress a hot plasma, even if it doesn't fuse very efficiently.
If it has a low nuclear cross-section of influence, yes. And then there's a third one, which is the amount of energy input to the particle accelerator, which is 1 mega electron volt. That's 1 million volts. And they capped it at 1 million volts originally with the particle accelerator regulation. The reason why...
it was a cap,
it was around 1 million volts. The reason they don't want you to go above 1 million volts is because if you go above that, you start transmutating other things in the area.
Yeah,
there's a cross-section that grows, right?
Yeah.
And that's the part where it's really interesting, because in 2023, the FIA and Halion wrote a letter to the NRC requesting that they do an amendment to the particle accelerators to increase the mega electron volt input to way further. And they made a change to the handling of the nuclear waste that is created from the fusion reactor.
It sounds like that might have been motivated, purely speculation here, that might have been motivated by a desire to avoid having to come up with a new classification of equipment or device to accommodate what they're building. So they needed a little bit more headroom to keep it as a particle accelerator and avoid more, I guess, bookkeeping or regulatory mess to kind of organize.
Well, I think what happened there, Bryton, was that the engineers said, we're going to make a, inertial confinement or reverse field confinement or whatever the engineers did to make their reactor. They said, these are the parameters.
So,
and then the rules, when they got dropped into the NRC rules, they're like, oh my goodness, our engineer designed correct.
We don't have a classification.
We're actually outside the zone. We better make an amendment.
Yeah.
And I say, if you're not within the classification of a nuclear cross-section, I almost said it, cross-section.
Crocs-section.
My Crocs are so sweaty.
Putting these in sport mode.
But if, what they did there was they moved the goalpost a little bit. The engineer said, we don't want to change the voltage input. We want to just keep the voltage as it is originally. But we're going to change the rules so that we fit in. The cog fits in the wheel, right?
Right.
Instead of trying to change their reactor to be in that rule set.
Right. Interesting. I'm going to have to go back and read that a little bit more. I wasn't sure. I guess I was thinking they were talking about the energy levels of the radiations that were coming out.
It's the input power.
Okay.
It's how much. It's like when you pull a rubber band back. You can pull the rubber band back this much and you let it go. That's going to have a nuclear cross-section potential output. For every input, there's an output.
Right. It's like, how far are you reaching with this thing before it gets absorbed in the environment?
Right.
So you want to avoid that spreading out too far.
Yeah.
And that's something that we talk about. I think we've talked about that in the past with Skyshine.
Ooh.
Where you can have radiation.
Tell the audience what Skyshine is.
Well, Skyshine is basically where you have an emission event, you radiate, and it goes up into the sky and hits some clouds or
what's radiating
first?
What comes off first to cause Skyshine?
I forget the exact radiation.
Neutrons.
Oh, it's specifically fast neutron flux.
Yeah,
so you get fast neutron
go
flux going way out into the environment, up into the sky, and when you hit stuff with neutrons, it can become radioactive also. So you can, and you have a lot of secondary and tertiary scattering.
Yep, that's right.
So you hit the air up above your facility with a bunch of fast neutrons, and it re-radiates downward.
Yeah,
as well
X-rays.
As in all other directions, but it sends down X-rays.
Yeah, it shoots neutrons up, and then it hits the air, and the air absorbs it. Right. And then the electrons get compound nucleused, and then they emit X-rays down onto people's heads. And
so you have to shield over the top of your reactor, not just around the sides of it.
There was actually a case, there was a friend I knew who worked at an X-ray department for a medical company.
Yeah.
And one of the operators there that had been there for like 15 years, he got brain cancer. And the shielding didn't have a roof shielding. So they were shooting the patient's X-rays for the stuff they were doing. And the guy was getting freaking sky shined. Bam. Man, he didn't know it. No one knew.
Yeah.
And then he got brain cancer, and then they did it. They were like, oh, we better put shielding. So when you do a nuclear cross-section event, you have to expect renormalization in the entire universe. You have to account for that.
Yeah. These radiations have the potential to reach out not just in a straight line fashion in all directions. You can't just shield against one direction and think you're fine. There's a lot of stuff that can happen outside of a facility where you're running nuclear tests.
Nuclear fission, nuclear fusion, and that's where we're really excited about our technology here at Quantum Kinetics, is because we're using safe nuclear processes. And by the way, Bryton, we just got the trademark from the United States Patent Office granted to us for safe nuclear. So that's, cheers, buddy.
Fantastic.
Like that's so great.
Another one.
Mm-hmm. So yeah, I just want to let you guys know that we're making really great progress, and we appreciate all your guys' help in getting this far. And if we continue to have this kind of momentum, we're going to be changing the world pretty soon, Bryton.
If there's one thing we're good at, it's coming up with cool names.
Are you tooting your own horn?
There's another thing or two in there too, I think. But
I just love Randall's ability to make great slogans. He's like, cold neutrons are hot. Like, dude, that's awesome.
He's definitely the slogan master around here.
Man. Yeah, he's pretty awesome. We love him so much. Thank you, Randall. So is there anything else you want to talk about in terms of nuclear cross-section, waves? What do you want to have any discussion about, like... I want to ask you a question.
Oh, go for it.
I want to ask you a question.
I get to step into or sit in the expert chair for a minute here.
Well, it's a theoretical question.
Oh, never mind.
Let's say you were given $67 million. Okay, and you were, hey, you got to make a nuclear reactor that's fusion, that is deployed for mining and also transmutation. Let's just say you got a contract at Fukushima. Fukushima has 132 million gallons of tritiated strontium-90 radiated water from their reactor that blew up in 2011. And someone gave you $67 million. What would the reactor look like to start treating that water? Like, what would it have in it? What would it look like? How big would it be?
Well, I know what part of it would look like immediately, because we've done experiments with this already where we know that we can use one of our reactor configurations to reduce concentrations of heavy radioactive elements. And we can pump the fluid through the reactors at a certain rate. It's a pretty low flow system. It's like 30-something gallons per hour that we can flow through it. We have to circulate it over time to make this reduce substantially. We have some optimization to do, but I bet we could fit this thing into probably an intermodal container that could be rolled up. And
what kind of size intermodal container would it be? Would it be like one of the smaller 20s footers, or would it be like a 40 footer or bigger? What would it be like?
Well, I wouldn't want to spend all of the money in one go, because you've got a business to set up and get running smoothly administratively. So I'd probably start a little bit smaller with like a 20-foot unit.
Okay.
And
so that would be like a milestone project.
Right. That would be an excellent milestone project, and also a platform for optimizing things, because we've only run these tests so many times because it's expensive to do setup.
Do you know how? Well, I can't actually disclose the number, but it's very expensive.
Yeah, it's pretty pricey per setup to do
radioactive waste.
Radioactive anything. When you start dealing with running water that has uranium,
poison,
uranium in it. First of all, the people with uranium you don't have a whole lot of people that are able to help you with those sorts of things.
Right.
So you have to do these things with a lot of care, and the inputs are expensive. The setups are expensive. You have to have very technically qualified people.
Oh yeah, certified.
And to manage this process for doing the experiment. But I'd say with that range of money, we could definitely get out a test unit and be running it.
Yeah.
And we already know that it's successful. We know it works. But that would give us the ability to set up and run, optimize, and be prepared to actually scale it.
Oh yeah.
And start deploying it to a lot of places, because we have a lot of sites. We have Fukushima. We have, in our own backyard, we have the Hanford site, where they have a lot of these similar water-bound
goo
or
weeping out the
slurry,
concrete.
or I think, and some of these are also just dirty water. It's not really like so slurry. It's not really like a high concentration of solid material in a lot of these cases.
A lot of it's just iodine, strontium 90, and cesium, and there's definitely uranium in there, because we actually tested the Columbia River water ourselves, and we detected it. So it's there. Yeah, right. So that would be an amazing place to be. I'd love to have. There's a lot of good golf over there.
I'd love to have tens of millions of dollars to play with. But that would get us a long ways. I'm very confident that we would quickly have a functioning
timeline. What do you think?
Functioning total package unit that would be pretty much plug and play. And we've gone through these mental exercises and done some of the initial design stages of that stuff already. And with my mechanical construction background, I have a pretty good understanding of the technical requirements and the likely timelines. Sourcing equipment, how to talk to people to get this thing put together in a smooth fashion.
We're so excited because you know how much money...
We're getting there bit by bit,
Do you know how much money the Japanese government has assessed that just the tank water, the treated tank water, is going to cost the government and the people over there in Japan?
It's like 220... Was that B?
It's a
billion?
B.
Yeah, $220 billion.
$20 billion for that water. And the Government Accountability Office of America for Hanford, they've done a calculation, independent study, saying that the Hanford site itself could range anywhere between 220 to 660 billion, and they don't even know the timeline for when it's going to be done. And the same thing happened with the Japanese government. They said it's going to maybe cost 660 billion. So all government agencies that are talking about trying to clean up radioactive waste, they say the same number and they say the same thing. We don't know when it's going to be done because they don't have a solution yet. No, there is no solution except for this right here.
Yeah, this is the only solution we know of. The problem with that is all of these estimates of cost to the public for handling this waste is that these materials are not being changed. They're just being stored. And when that radioactive material destroys the container over time that it's stored within, it has to be put into a new container. So it's just this ongoing cycle of moving it from one place to the other, and then back again, and then back to the second spot, and then back to the original spot, and kind of shuffling it back and forth.
It sounds awful.
Because most of these, or actually, not most, but a huge amount of this radioactive waste is material that has half-lives in this range of millions and billions, thousands of years. We can't comprehend timelines like that, but they're present. So we for all practical purposes, these are forever materials that are just sitting there radiating away, and we have to shield it, and it destroys its container over time. So we just have to deal with these huge costs of going through that cycling.
Yeah, it's kind of a depressing thing to think about, that there is no solution. And I was just on the phone with one of our people that we work with who's very well knowledgeable about radioactive stuff and rad waste. He was saying that he was just recently at a conference, and the consensus is that nobody knows what to do. There is no solutions. It's just put a Band-Aid on.
I've got one.
Take a Band-Aid off, put another Band-Aid on, and I know Bryton here at Quantum Kinetics, we're itching and ready to go. We want to make a difference.
Right.
And we want to save everyone, At the end of the day, everyone has to pay for that. Like our tax money goes to paying for that cleanup. And if it's going to be 300 years or 400 years to eventually get this cleaned up, that's going to be a lot of money out of your pockets. Like you won't even be able to go buy TVs that you want or buy a car or finance a car. Like what we're trying to do here at Quantum Kinetics, we're just going to give you guys solutions to big problems so that at the end of the day, you have more money in your bank account. It's really that simple. And we clean up the world at the same time. And the great thing about as we do the transmutation with this gravity negative field is that we're mining at the same time.
Right.
Whoa.
Yeah. I mean, we're getting
awesome
useful stuff out of the reactor as far as material as just a byproduct, which we have some control over already.
Oh yeah.
We're cooking right now, when we have the chance to optimize it, we'll unavoidably get better at this.
What's crazy about, I'm sorry to interrupt you, but the really cool thing about the seawater of the treated water in Fukushima, it's ocean water. And when we put ocean water through our reactor, we get more sedimentation. Right. We get more mineral fabrication of like nickel, iron, aluminum, magnesium, silicon, all these crazy cool elements start showing up tungsten. At a rapid tungsten. Well, yeah, it's small. I mean, maybe it's small.
We've had some of that.
And it's just so there. It's it's basically this awesome sludge that you can dry. And then you have this metal there, compounded metal.
Right.
How awesome, man.
It's going to be a fun process working through the details of like refining that stuff too, because that'll be able to be turned into a lot of useful stuff over time.
Lucky for us, most water processing centers already have the systems already made.
Yeah, and
like a baffle and all that stuff.
And we keep talking about money, but that's part of this game is that it's when you're bringing in something new into the world and trying to share it on large scale so that people will put energy and thought and money into it to build it, and confidence. A lot of the world really is like, well, if it worked, you'd have money. It's like, well, it's new, so we haven't gotten money yet on large scales. We love our investors.
They're great. Thank you so much.
We've gotten a lot done because of them.
So to go on that point, I met with one of our investors yesterday for lunch, and you know what he said? And by the way, this guy is a money manager himself, and we were having Thai food.
Right.
And he says, McKane, I have to tell you something. You have done amazing things on a shoestring budget. And I can't even imagine what you're going to do when you get the real money. That's what a money manager guy said to us.
Yeah.
To me yesterday.
It's like that. I've heard the term a bunch of times, but the S curve where it goes from like, all right, where things are going kind of slow. Now it's speeding up. Now it's going. It takes off before it kind of hits the long-term stability. But there's this range right up at the start of everything. Every new pursuit, every new business, where things are just like, all right, we're working hard, we're putting a lot of effort in here, and then it's starting to turn up, and I really feel like we're starting to hit the start. We're really hitting the start of that steep upslope on this one. It's going to be there before too much longer.
In the last 2 weeks, Bryton, I've gotten 3 different emails that have had offers to buy the company outright. And they said, schedule a meeting right now. Here's the link. We want to buy the company.
I don't want to sell this thing.
So when
I want to keep it.
Like when you're getting emails like that, repetitively, from different firms.
Well, that's a good sign when you start seeing those rolling in at a decent pace.
Yeah, and not just that, but we actually have people coming out now and emailing us saying, "Hey, we want to partner with you. We want to, put you on this show, or we want to do this with you." And it's really, it's awesome. Thank you so much for doing that because it's helping the movement grow. It's helping the collective consciousness wake up that this is not a pariah anymore. This is a real thing. Yeah. And I think, Bryton, in the next 4 months that this world's going to start changing, really, in a big, big way.
Yeah, it doesn't feel like we're hitting that barrier of disbelief nearly to the same extent that I felt we were seeing early on when I joined this one. And it's been an exciting process of getting there with that.
Yeah, and again, the more people that get involved, the stronger it gets. It's like a baby that just came into the world. When you make a baby come into the world, it doesn't even know how to eat. It's just sitting there crying, and it's cold, and it's like, you've got to like put a blanket around it, you got to start cuddling it, and you got to put a little beanie cap on it.
It's a lot of work.
And and you got to give it its shots and stuff to make it so it doesn't get sick. We have a new technology that's in infancy, nascent, they call it, stage, and it's starting to grow legs. Finally, it's starting to stand up. It's starting to start walking,
and it'll be running, but before too much longer here.
Yeah, and I mean, if we succeed, you guys succeed. That's the most important thing about this podcast series is one, education, telling you that you're going to win if we win, and it's going to be an amazing new world. And the technology rollout of this is going to save. Like I was just listening to Chris Wright, the Secretary of the DOE, this morning, and he was complaining about how Germany has been spending all this money on new technology and getting away from nuclear fission and trying to like find clean energy resources like solar, wind, and all this. And he was complaining about how expensive it is, and how it's not meeting the demand. Well, okay, if these things are not meeting the demand, which I don't disagree with, I think he's right about that. But then at the same sentence, he pushes oil. Well, we know oil doesn't work either because it's killing our planet. So we have to figure out a new solution, right? We got to come up with something different because these two things that we have right now are not working.
Well, another one of the great things about what we're doing is that one of our early focuses with this technology is very much the nuclear waste treatment, because that's something that's in our backyard. It's something nobody else is offering or really even talking about.
No one knows how to do it.
We figured out how to deal with it.
And patented and trademarked and copyrighted.
Like, that's a completely open niche. We have no competition in that space.
Yeah.
But with all of these nuclear fusion companies, they're all talking about power generation.
Electricity.
And our technology, because of its reliability and simplicity and efficiency, shows much more promise than the standard methods that have been kind of repeatedly refined and tried over the last 70 years. I mean, this is kind of the running joke around nuclear fusion is, I can't wait till they tell us it's 10 or 20 or 30 years out after they've been telling us about all this stuff and collecting a bunch of money to do it. And that's kind of been the story the whole time. And that makes sense. I mean, that kind of happened with this, like the Fleischmann and Pons story back in the 80s.
Yeah, and to go to the Fleischmann and Pons thing is that when we started this 10 years ago, we took this as the approach of an athlete versus a coach, right? Like I used to coach you in the pole vault back, 15 years ago?
Yeah, you were my coach for like a couple of years.
Yeah, and so when
dropped off the map.
Yeah, and so when I would teach my athletes, and what I learned from gymnastics is that when you fall off the horse or you crash out in the pole vault and you come over and talk to the coach is going to say, well, what happened there?
Right.
And you say, well, I felt like my run was off. And I say, your run was off and it was because of this. And then you say, oh, if my run is off, I let you coach yourself.
Right.
I help you.
A required bit of self-reflection there.
Yes.
That's required in any kind of development process where you're trying to improve something. The person who's trying to improve it, who built the thing, has to take a look at this and say, well, these are the things we're missing. And to me, it feels like academia and the fusion industry has kind of been avoiding doing that in a very extensive way because they keep coming back with the same answer of, we need to do more intense magnetic fields. We need to do higher currents and
higher voltage.
Yeah, higher voltages, which drive the higher currents. And we need to use different materials. And
More nuclear cross-section.
Right, we need to use a different fuel, we need to use different materials for the construction, and they're creating all these incredible technologies with the superconducting magnets, these giant magnets
They
that
can pick up
aircraft carrier. Yeah, I'm quoting
crazy.
somebody there. It's a pretty cool magnet. I like seeing that stuff. It's neat.
But listen to this. What happens if the magnet fails during operation? Oh,
that's a good question.
Oh boy, look out.
That's a good question. But the problem here is that it's been so long with such infinitesimal improvements in the actual outputs that it at some point it's like, come on guys, let's invest a little bit, like keep investing energy into that pursuit. I think they're making progress in a lot of ways that can be used for surrounding industries. Probably eventually for what we're doing too. We can probably apply stuff from that technology development they've done to our own.
Do you want to know what their process is really good for? Like the hot fusion colliding particles together like that is really good for making tritium.
Oh yeah, I mean that's
like a lot of tritium,
which is an incredibly valuable output. It's
$30,000 a gram, dude.
Yeah,
that's a pretty good industry.
There's not many things more expensive than tritium by weight. That's pretty incredible. It's like what 500. How many grams per ounce?
I don't know. I'd have to look that up, but
I knew this when I was managing my like nutrition for like weightlifting program. I'm like, all right, I got to get 500 grams of protein. That means I eat X amount of steak or eggs or something, but I forget that conversion ratio. But that's a lot. That's a lot of dollars per pound of material right there. But
it's good for making tritium.
Totally kicked off.
No, you're like,
track.
let's go back into pole vault.
I was
buddy.
like, I'm thinking about steak.
Well, steak is delicious, bro. So nuclear fusion, hot fusion is good for making tritium.
Since we're the alternative guys, we would really love to see some large scale funds going to different strategies to see what turns out. And I'm excited to see that start happening. I think we're at the cusp of it.
Yeah. Again, like if there is there's a little bit of money that can go a long way with this movement. I'll tell you why. Is because the technology is figured out. There's no more real true research to do. Maybe a little tiny bit here for something of particular value that we're not going to talk about to the public yet. But in terms of radioactive rad waste cleanup, that's figured. It's good to go. And the beautiful thing about it is it's basically the same as a water processing plant that we've already figured out in terms of like, what are the resources you need? What are the tanks you need? What are the pipe fittings you need? Are they ISO certified? All these things, like all that's already figured out. Like that industry pipeline is already developed to a very high level. And all we have to do is get into that pipeline and then add in our reactors with the plumbing and the fittings. Yep. And that literally is all that's necessary. Yes, there's a little bit of extra safety with IAEA and the NRC and all these other things. Like we will comply with that.
But that's stuff they've also already figured out for nuclear fission. We've been building those reactors for longer than we've been building fusion reactors, and they had to figure out radiation safety for that.
It's good to note.
We have a lot of people around who are very good at that.
It's good to note that the nuclear fission industry with the NRC rules is a lot higher regulated than particle accelerators. Particle accelerators are like infinitesimally tinier regulation than, say, nuclear fission. The reason why is because if something happens in nuclear fission, it's way worse.
Right.
It's like way worse.
And nuclear fusion hasn't been developed into a system that's been applied for years in an industrial environment where they've had, because regulation, codification of that stuff takes time. And fusion is not going to be the same as fission. There's some similarities, and we figured out a lot of that important stuff with shielding.
Yeah.
And secondary containment processes, and construction methodologies, quality control methods. All of these are very important and also very well worked out. Like,
we just have to get in the pipeline. I mean, it's like if you're a surfer, you got the board.
Right.
Just go swim out there and get a wave, and you're on your way, and you're going to be the best looking surfer who's going to win the competition with barely any input.
Yeah.
And by the way, the first person to put money on this is going to basically be probably the most famous people on the entire planet. I mean, we're literally that close.
It's another one of those things where the first thing to really take off, or one of the early ones to really take off, when you think of the big names and big companies, you think of like
Westinghouse, right, or
AT&T, IBM, Microsoft, Apple. Like these are all companies that Westinghouse. Well, even further back with the proliferation of early electricity distribution and generation. All of these companies are companies that form at the start of a new technology and catch that wave.
Yeah.
And we, I think, are one of those companies.
Oh, yeah. For sure.
Really exciting times.
And so we're coming up on the closing here with up to an hour, so we're going to have to close up.
We got carried away there.
No, I think we did great.
Yeah.
And to go on the last point there is like, essentially, whoever helps out in this big way is going to reap some really big benefits. And I will say this, that cold nuclear fusion has never gotten this far in human history. And literally, you could wake up in a week, you could wake up in a month, you could wake up in 3 months from now and look at a headline and be like, it's a done deal.
Right.
That's how close it is to changing it's called a quantum loop. So when you're in a quantum loop, you're stuck in a memory loop of like, this is the way things are, this is the way things are, this is the way things are. Literally, we're literally like a hair. Yeah. We're one hair's length away from getting out of a quantum loop of destruction. We are so close. And it is so exciting. And I'm so thrilled to have you and Randall and everybody else that is out there helping out. You know, it's awesome. You guys are wonderful. And we're working for you guys. We're working hard, and we just want to say thank you. Make sure you like, share, and subscribe the channel to everyone you know, because this movement is going to change your world for the better. So, well, any closing thoughts?
No, I think that pretty much sums it up. This is going to be real exciting.
Yeah. All right. Well, thanks for coming on the show, Bryton. It's always nice to have you on, and thank you for the lesson. Appreciate it.
Always a great time.
All right, everyone. Have a great rest of your day, and we'll talk to you soon. See you on the next one. Take care.